Physics 2015 Lab 9, Rotational Motion. In this lab, we hope you will become familiar with the terms rotational inertia, rotational energy, and angular momentum. You are already familiar with many linear quantities in physics, such as mass, distance, velocity, acceleration, momentum, and energy. These are considered linear when they are used to describe motion in one direction along a straight line. When we need to describe rotational motion, each of these linear quantities has an analog that we use. Instead of mass, we have the moment of inertia, usually shown as the capital letter I. Instead of distance, we have an angle, given as the Greek letter theta. We have angular velocity instead of linear velocity, given as the Greek letter omega, and angular acceleration is shown as the Greek letter alpha. Angular momentum, capital L, is the product of the moment of inertia and the angular velocity. Notice the similarity in the equation for linear momentum. It is the product of mass and velocity, which are the linear analogs to moment of inertia and angular velocity. You will notice another similarity between the equations for rotational energy and linear energy. Understanding that these rotational quantities are analogs for the linear quantities you already know should help equations such as the ones for angular momentum and rotational energy make some physical sense. Moment of inertia might be a particularly new term. The moment of inertia of an object is the measure of how resistant it is to changes in its rotational motion. This may seem a bit abstract, but if you think about it, so is the idea of mass. Mass is the measure of how resistant an object is to changes in its motion. This resistance to a change in motion is the object's inertia. The moment of inertia, then, is just a special case of mass in the context of rotational motion. Newton's second law tells us that force equals mass times acceleration. An object with a greater mass than a second object requires a greater force to change its motion or accelerate it by the same amount. Similarly, an object with a greater moment of inertia requires a greater rotational force or torque to change its rotational motion by the same amount. Just as there are analogs between linear and rotational quantities, many of the laws of linear motion have counterparts for rotational motion. Newton's second law, as we are usually familiar with it, says that force equals mass times acceleration. In rotational terms, we find that torque equals the moment of inertia times the angular acceleration. Kinematic equations for constant acceleration have counterparts for constant angular acceleration. The law of conservation of momentum says that if the net forces in a system are equal to zero, then the momentum for the system remains constant. Similarly, for conservation of angular momentum, if the sum of the torques is zero for a system, then the angular momentum stays the same. This lab has 3 activities in which you will explore rotating bodies and conservation of energy, collisions between rotating bodies, and the scenario of the spinning ice skater. In the first activity, gravitational potential energy will be converted to rotational kinetic energy. You will measure how well energy is being conserved. Make sure you understand what these 2 types of energy are and what it means for energy to be conserved. Also, consider other types of energy that might be relevant. It will help if you are able to figure out how the angular velocity of the smart pulley is related to the rotational velocity of the platters. For activity 1, set up the apparatus as shown in this diagram. One end of the thread should be connected to the smallest spindle of the rotating disc, and the other end should be tied to a given mass. The thread should extend horizontally from the spindle and then drop vertically over the pulley clamped to the table. When the thread is extended, the mass should not touch the ground. In the second activity, you will design an experiment to show whether angular momentum is conserved in collisions between rotating bodies. You will need to remove the thread, extra pulley, and mass from the apparatus. Then turn the main platter upside down so that the spindle is on the underside. Activity 3 is called the spinning ice skater. In this activity, you will use a rotational apparatus to model a spinning ice skater, and you will determine whether angular momentum is conserved in this situation. You will have masses that ride on carts which fit inside the U-channel. You will place the U-channel on the apparatus as shown in the diagram. Connect the masses with a string that you will thread through the center of the axis of rotation. When you pull on the center of the string, the masses should be pulled toward the center of the rotating platform. This models an ice skater bringing her arms in toward her body as she spins.